Okay, ladies and gentlemen, turning points.
Turning points.
What is it? What is in calculus?
Turning point.
Let's have a look. So on this sketch I've done, we've got some turning points on here. It's basically when the gradient goes flat, so it's going up or it's going down, and then it's going up and then it starts going down. So it's a turning point where it goes flat. There's one there, there's one here as well. There's one here. Okay, and they're turning points. You know what's significant about those in relation to calculus? Differentiation. You know what's significance?
The turning point is 0.
Yeah, the gradient is 0, yes. So the d, if this was y and x,
Equal to 0.
then it would be equal to 0. As we'll see in a bit, that's really useful. It's used as a tool in calculus to solve problems, as you'll see. So they've all got that in relation.
Yeah.
Okay?
Yeah.
So it doesn't matter, it doesn't have to be the highest point. This one's higher than this, but it's still a turning point. And it doesn't have to be below the line, it could be another one here like that, couple there.
So why is not minus 0 so much? Because it's under the line?
No, because it's actually 0. Okay, so there's no gradient at all there, it's flat. We call this one a maxima. So you've heard of a maximum, this is a maxima, this is like the Italian version, mal instead of mon. Okay, and guess what, this is called a minima. Very imaginative. Okay.
Maximum.
Now what we've also got on here, though it's not obvious, it's not very clear, you get it with a sine wave. So if you've got a standard sine wave, you've got that on there. Something called an inflection. Now an inflection's got two spellings. Inflection or inflection. Both are correct. I don't know which one came first. I only knew the second one for years and then I came across the first one and thought I'd spelt it wrong. It turned out it's correct. An inflection is a peculiar thing. It's when a gradient, so if I'm zooming on this, basically I've got this. So it's this point here, when the gradient, instead of going, it's going that way and then it starts going that way, so it's where it changes direction. So it's not a 0 point. It could be a 0 point if you tilt it enough, so you can have that. I can't really draw it, I can't go that way. You can get one that has got a zero gradient, but generally, like with, for example, with a sine wave, cosine wave, it isn't. It's not 0. It does still have a gradient. It's just that the curve has changed direction. So it's curving this way, it's not curving this way. So that's called an inflection. Okay, so that's important because you'll be asked for that. Because you're going to do a sine wave sketch and you'd have to label the parts, so where the inflection is, etc. Okay, so what will we use it for? This will, I think the best way is an example. So I'm going to rub this off. You've got enough what you need there? Put that down. So I'm going to rub this off as well. Okay. Excuse me. So picture a drinks can, like a Coca-Cola. There are other brands available. We say a drinks can. There's millions of these made a year. I don't know how many. I once looked it up and I've forgotten, to be honest. But there's a lot of them made out of aluminium. Now aluminium is fairly expensive material. Relatively speaking, it's a lot cheaper to recycle it. But if you make it from new, I think I did once see it was about 11 times the price to make it afresh than it is to recycle it. I think at the minute though, I think they do have to make aluminium drink cans It's an alloy actually, but I think they do have to make them from pure material, so there's no contamination in it. So you can't use recycle if that hasn't changed. I know those rules are starting to change because I know that it's happened with plastic bottles, hasn't it? PET bottles. Quite expensive. So if you can use as little aluminium as possible, you're going to make your profits bigger, especially when you're making millions at a time. So if you can use less aluminium, you'll make your profits better. One of the ways to use less aluminium is to use the optimum shape of can. Now this doesn't apply in every case, because if you get something like Red Bull, it comes in quite a thin, tall can, and that's not an optimum shape, but they do that for marketing reasons. So and people are daft enough to pay the higher prices anyway. So it doesn't matter that it costs more to make it, because they're making enough profit anyway. I mean, how can a company exist that only does one thing?
Yeah.
And how can they support Formula 1 racing on it as well? You know, it shows how much profit they're making. Anyway, so one of the ways to is up your profits anyway, besides that, is to make your can an optimum size. So what do I mean by optimum size? Well, if you think about it, you can make your drinks can. It could be long and thin, like a long thin tube, almost like a straw. Now imagine if the hole in the middle was really small, like a straw. Imagine how long it would have to be to hold, say, the amount you want to hold. Let's say 200 millilitres. Let's say 200 millilitres. So you can imagine the size, how length it'd have to be. So that would use a fair amount of material.
Yeah.
Even more so as if you go the other extreme. So if you go to the other extreme, like this, like a big disc, with a thin gap. It's a bad drawing, but a thin gap between the top and the bottom. You wouldn't get a lot of liquid between them two layers. If you got the gap to about, say, a millimetre, 0.1 of a millimetre, can you imagine how big the disc would have to be to hold 200 millilitres? So that would be the worst scenario. That would use a lot of material. So what you get, if you plotted it, so you plot your size, so you've got your surface area and you've got your radius. So as that radius changes in size, you're going to use quite a fair amount of material down here, then it's going to decrease. Then it'll start to go back up, and then it'll get a bit daft, and then probably start to flatten off a bit. I'm not sure without plotting it. But here, we've got a turning point, we've got an optimum point, a minimum.
That's 0.
That's not zero, the gradient 0, yes. You've still got a radius, obviously, but that's your optimum for your drinks can. Now this principle can be applied in lots of things, and is applied to lots of things in engineering. So optimum performance of an engine, and you might, obviously the calculations might be a bit more tricky. We'll see some examples actually, and I have got some examples on YouTube as well, on my videos, different ones, that tie in with the assignment, by the way. And if this goes well, we'll have some more. Okay? Right. So what we're going to do is we're going to come up with a way of finding this optimum, and that's where our differentiation comes in. So I'm just going to rub all this off. I'm going to redo this graph because it is relevant. So I'm going to keep this over here. Something like that. So surface area against radius, and we're looking for this R value there, the optimum radius. So what will we do? So we've got a drinks can. Something of that nature.
What is that shape?
Just typical shape. It might be longer, it might be shorter, we don't know.
200 ml.
Okay, for 200 millilitres, yes.
Yeah.
Volume equals 200 millilitres.
Yeah.
Siraj, guys, so 200 millilitres. So we're going to find the optimum radius to give us this size. So obviously it's got a top on, because you've got to have a top on it, but otherwise your Coca-Cola or whatever you might be drinking is going to go off and it's going to lose its fizz and it's going to spill. Okay, so you've got to have a lid on it. So it's got top, a bottom and sides. This is a generalisation because obviously drinks can's a bit more complicated. If you look at a drinks can, it's shaped to deal with the pressure of the gas in it, the CO2. So it's got a dome on the bottom, hasn't it?
Yeah.
And then the sides have even got a bit of a curve in them, and it's got a shape that makes it a bit more rigid. Well, they press them out of one piece, don't they? And then they put a top on that's sort of riveted on, I think. I don't know. It's got an edge on it, and it formed. And that also helps with the stiffness. And then they can stack them as well. That's the other benefit of the shape. So there's more to it, but keeping it simple for this. That's the idea. So what I've got to do is I've got to come up with a formula for the area against the radius, and then I can differentiate it. So I can, if I plotted that with that formula, I'd get that shape. If I differentiate it, I can find where the turning point is. I mean, I can do it on a graph as well. I can draw the graph and look for it on the graph. And that's not a bad method. But generally speaking, calculus, differentiation is usually quicker than the graphical method. You could also do it by trial and error. Try loads of different values, and then you'd see it's going down, then it starts to go up again, and then you go between your values and optimise it. But that's obviously long-winded. That's not your best method at all. So we're not going to do that one. Okay, so what would be a formula for area, the surface area of this? I'll just call it A.
Oh, yeah, that's good.
What, your area for all of it?
Yes, for the cylinder. What's the formula for finding the surface area of a cylinder?
Pi r squared times height.
Pi r squared times height. And that gives you what?
It gives you the area of the top and then height.
I think what you find there, you find the volume.
Oh.
But see, now you've said it, we'll use it. Yeah. So that's your area of your base times your height. That's your volume, actually. So this is good. You were going the right way. Area is not that far removed. With the area, we've also got the base, haven't we? You've got the area of the base.
Oh, right.
So that bit's correct. But what else does it have? Well,
Pi r.
it's got a base, but it's also got a lid. So it's 2, yes, 2 pi r squared. And then it's got the side, the bit that you can roll around. Okay? So that's got the circumference, and it's then got your height. So what formula would I use for that? What would that do? Describe the side. So it's going to be added to it. So if you're making this in the fab shop, you get your piece of sheet metal and sheet. Yeah, pi r h, yes. Is it pi r? 2 pi r, yes.
2 pi r h.
Because you say, to find the circumference, the general formula is pi d, isn't it, the diameter,
Yeah.
but we want the radius because we need to get it into terms of radius. So we don't want another variable like d, so we half it basically. So we've got 2r. Okay? Right. Good expression. The only problem with that is we've got a h in it, we've got two unknowns, we've got the radius and the h, because they both change. So as your radius changes, your height goes up and down, doesn't it? So what we've got to do is get rid of something, one of the unknowns, and I would suggest that h is the best one, the easiest method. So we need to get rid of the h. What's the best way to get rid of the h in there? This is where this formula comes in.
Okay.
So, what I can do.
Replace it with the volume.
Yeah, we know what the volume is, so V, we know what V is. So we know that V equals
Swap the formula around a bit.
2, yes, exactly, swap the formula around, yeah, perfect. So 200 equals pi r squared h. So if I rearrange this in terms of h, I can then substitute it into here, and then get rid of h basically. So substitution is a good method, used a lot in physics, engineering, maths, to get rid of one of the unknowns. You can do it with your simultaneous equations, that's one of the methods. Probably not the easiest, not usually the quickest method, but it works. So we rearrange that. So if I do this over here, if I rearrange this into terms of h, I'm going to have h equals 200 carry these to the other side.
Mm-hmm.
So
Divide.
pi r squared. Yeah, divide through basically
Mm-hmm.
to move them to the other side, leaving the h on the other and then obviously swap them around. So I can then take my formula there. I'm going to put a circle on that because that's going to prove to be useful again later on.
Mm-hmm.
I can now substitute that into h, so I will have area will equal 2 pi r squared plus 2 pi r, and then in brackets, substituting for h, 200 pi r squared. Yeah?
Yeah.
So what's next, Marnie, what's next? What am I going to do with that? Right, well, before we get to that stage, when you get into with brackets with things outside of it, it's the usual practice, good practice to get with the bracket, multiply out the bracket. That usually simplifies things. And quite often, like in this, it's going to get rid of some terms as well, which will make life easier for us. So that 2 will multiply into that 200, making it 400. The pi will multiply in, but then cancel with this pi. You'll see that? And the radius will go to the top, so I'll have 1 r at the top and 2 at the bottom.
So it'll be 400 over R.
Yes, perfect. So it'll be, as you rightly said, 400 over just 1 r left, 1 radius. So that's a lot simpler. Now what I can do with this as well, I'm ready now to differentiate it. But to make it I can't differentiate this the way it is, so what do I do to make this?
So you said that R goes to the top?
Yeah, I'm going to bring the r to the top so I can differentiate it.
Mm-hmm.
So what would that make that into? Remember your laws of indices? Bring the r to the top, but I have to do something to it. Yeah, minus 1. Minus 1.
By -1.
So I can now, because that's your laws of indices, if x, 1 over x, is it the same as x to the minus 1? Remember that? So I can now differentiate that. So it's going to be dA, dr. So what would this become, this term? I'll throw my pen away.
Yeah.
What would that become? This term?
Four.
Yeah.
4 pi r.
You all know.
R
Yeah. The 2 comes down the front, as always, multiplies in.
plus.
Don't be confused by the fact there's a pi there, it's just another number out front that we can't well, you could multiply it in if you want to do the maths, but there's no point, just make it confusing. And this one, differentiate that, what will I get?
Minus 2.
Yeah, it's going to become minus, it's just going to change this to minus 400.
R.
What about the what's that going to become?
-2.
Minus 2, yeah, minus 2. Yep.
Mm.
So I've now got an expression that will give me the gradient at any point on my graph. But what we're looking for is when it's 0. So basically, if I put this into put my numbers into a calculator, I'll get an answer for gradient, whether it be 10, 100 or 0. So I'm going to make this equal to 0. I could write when dA, dr equals 0. But I'm running out of space. Let's go over here in a minute. So if that minus that equals 0, that must mean that this term here is the same value as that one. Or that one's the same as this one. For 2 equals 0, it's like 2 minus 2 equals 0. They've got to be the same, but one's got to be opposite signs, obviously. So that means, I'll do one of my therefores, that 4 pi r must equal 400 r minus 2. Let me bring that minus 2 down here, because I'm going to rearrange it and it's easier that way. So having moved it up for calculus, we move it back down to rearrange it. So I'll do it over there. So what am I going to get if I rearrange that? I'm going to get r to the 3 will equal 400 divided by 4 pi.
500 equals 600.
Sorry?
No.
Oh, right. So that, obviously that 400 will cancel with that 4. So I'm going to get,
So why did you do R3?
because this R2 will come multiply through to the top of there, so I'll end up with R3, R1 times R2 ends up being R3. We don't want to do it like that though, we want to get rid of the 3, so I'm going to have to cube both sides to get it through. In other words, that 400 over 4 become 100 over pi, and then I'll have to cube it. Actually what I'm writing there is nonsense in a way.
Which is
Okay?
mm-hmm.
So if I cube that, I've got rid of my power of 3 there. So if I put that in my calculator, what will I get? Somebody want to tell me? Did you get the same as me?
What are we going to do after R4?
Cubed it. So
What I'm going to do after that, R4?
No, it's like, is that the answer?
It's going to give us, yeah, it's actually going to tell us the optimum radius. Simple as that.
3.17.
3.17.
Mm-hmm.
That's rounded. I got 3.169, but
Yeah.
near enough. We'll leave it like that, that's fine. Okay, so that is my radius. That is my optimum radius. That's the best I can get. Turning point and get the least amount of aluminium, the least amount of surface area. If I'm making a cylinder, what other measurement do I need? Suraj? If I'm making a cylinder, what other measurement do I need? The height, yeah. So how do I find the height? How do I find the height? Subtle hint.
Substituting.
Yeah, take that, substitute into this, and I'll get the height. So the height will be 200 by pi, so times 3.17 squared. Anyone want to tell me what that is?
6.335.
It is indeed, yeah, 6.339 I got, but depends how much rounding you do.
Yeah.
339, I'll go for 34. Is that 3 or 5?
It's 3, isn't it?
339 I got. I did this, I didn't round this.
So what do you round that to 6.3?
In fact, I might not have rounded it at all. Not if you're using 2 decimal places.
Okay.
So, that is my height. Another question there. What units are we in?
Centimetres.
Yes. Because you'd have to, you won't necessarily know this off the top of your head, that is equivalent to 200 centimetres cubed. Okay, so we don't have to change the units. I should have said this right at the outset really. We don't have to change the units into metres, for example, the SI units, because as long as we keep, we've said this before, I mean, as long as we stick with the same units all the way through, this length, this is a length, but it's a length cubed, that's what volume is. We're going to get this in centimetres. Okay? There's just one other thing we need to do. We've made an assumption, and it's a reasonable assumption, that this is a minima. We don't know that it's not the other way around like that, and that we've actually found the maxima. Right, it's illogical, probably, but you can't assume anything. And in a lot of circumstances, you wouldn't know either. You'd be working a bit blind with it, which way it's going, which is the maximum, minimum. If you've got various answers, for example, as you'll see when we get to a sine wave one. So I have to test it Now to test it, perhaps the slightly longer way, what we'd be looking for, we know this gradient here is 0. If we move to the right, we'd get a positive gradient. And if we move to the left, we'd get a negative gradient when it's going down. And vice versa for the maxima. So one method to test it, it's probably the safest method to test it, is to move slightly to the left with a value. So this is our radius, this here is 3.17. If I move slightly to the left and I get it going downhill, a negative, then that'll tell me. So for example I could use 3, so I put 3 in my formula here to see if I get a negative. And then if I want to find, because it could also do this, the shape could do this, it could go along, go flat and then go down again. Okay? So there's another kind of complicated kind of inflection where you still get a flat, but then it goes down, continues to go down while you expect it to go up. So if I move to the right, so if I could say, for example, put 3.5 in and see what I get, and see if it's a positive. You can probably, often you can see it by just looking at your numbers, though not so much with this one. But you'd have to, so what you do is, where R is in your formula, you would substitute into there 3 and see if your number is negative or positive. You don't care what the number is, you just care is it negative or positive. And if you get a negative, then you know it's going down towards your 0. Then go to the right and put in, say, 3.5, 3.2 will tell you actually, 3.2, whatever you want. Put that in and see if it's going uphill. We're not going to do it unless you particularly want to, because I'm going to show you another method that's perhaps a little bit quicker. It would actually give you this, it would give you a negative there and a positive there. Okay?
Yeah.
So that's one method, and sometimes the best method actually in some circumstances. The other one is what we've just done earlier, double differentiation. Double differentiation's got another use. So if I differentiate this again, and we'll get an answer when I do, let's have a look. So d2a dr squared equals, so I'm differentiating this again, so what happens if I differentiate this again? So it's nothing special, all you do is differentiate it. So what's 4 pi r differentiated?
4 pi.
4 pi. So the r's gone this time. And this one is where we've got this negative multiplying this, it's going to be positive, which is relevant.
So plus 800 r.
Yeah, so it's 800. Yeah. And then the r becomes to the minus 3. Now the significant thing here is, we only care about one thing again. What we would do is we'd take our radius and substitute into where there's an r, which is only 1, put it in there, do the maths, and we'd get a positive number or the negative number. Now that number, that sign of that number tells us if it's a maximum or a minimum. Now the beauty of this is a plus and this is a plus. So whatever number I put in there, I'm going to get a positive value. Okay? So that will tell me that it's going to be positive. Now with this testing method, it's not what you expect, it's the other way. You'd think that a positive would give you a maximum, but a positive gives you a minima. Okay, and if you get a negative, it gives you a maxima. So a negative, let's write it down here, negative equals minima, maxima, sorry. So the opposite to what you feel it would be. So that's all you've got to remember really, it's opposite to what you think and then you know, you remember. So that's what you would do. If this number had been, if this had been minus and this had been minus, we get a minus answer, so we won't need any further work. Again, we just know, we don't have to do any number crunching. The only time you have to do it is if one's positive and one's negative, and then it's the old case of which one's biggest, which wins. So, you know, bigger negative number, so to speak. I know it's smaller in some terms, but the bigger negative number will make it a negative answer, for example. And that's all you got to do.